Howdy folks, welcome back to another CS 120 Anonymous lecture. In today's lecture, we'll be focusing on parallelism and concurrency in Rust. So first, we'll talk about the motivation behind threads and why you'd want to use them. And then we'll discuss how to spawn threads in Rust. And finally, we'll talk about how to join threads together at the end of this lecture. So first, let's talk about what actually happens when you run your Rust programs. So your computer will create what is known as a process, which is an instance of some running program. In Unix operating systems, a process is started when a program is initiated. And how could we make these processes faster? That is what we'll be focusing on for this lecture and the next coming lectures. Should we just make bigger CPUs or chips? And how could we make bigger CPUs? Could we make the transistor smaller so we can pack more onto a chip? Or maybe we could make the CPUs physically bigger and add more transistors that way? Well, there's this theory called Moore's law that states that the number of transistors on microchips is doubling every 2 years, which we can kind of see from this graph. So in theory, this means you're doubling your computing power by adding more transistors. And while this was true for a while, recent processor speeds have sort of tapered off. So you can see in this graph that single-threaded performance and frequency have both started to taper off in the recent years. But what is rising drastically is the number of cores in a CPU. So multi-core processors are essentially circuits that have 2 or more processor cores on the same computer. These processors enable us to do more powerful types of computing, such as parallel processing and multi-threading, because they allow us to run multiple programs at the same time. So you're essentially running a program separately on each processor. So if you had 8 processors, you could run up to 8 things at once. But how would a multi-core machine help us speed up a single process? If it's still one process per processor, how do these cores help us speed up that one process? Well, that's where threads or threads of execution come in. They represent a sequence of instructions that the CPU has and will execute. So when you run your main function in your Rust programs, main is your main thread of execution. It has a sequence of instructions for your CPU, which will execute that code. So threads are useful when you want to leverage the power of multi-core systems to do one single task. So each thread has a main method. And if you have a single program that has multiple threads, it has multiple main methods for each thread. So you can run that same program on multiple cores at the same time, which allows us to run more code in the same amount of time as a single core. So these threads allow for both parallel and concurrent code execution. But what is parallelism and concurrency? Well, concurrency is simply multiple computations happening at the same time. So it's running multiple tasks at the same time, but all of them are starting and ending at different times, and there's no real specific order. If you open up your task manager, you'll see that your computer is running a bunch of different and separate tasks that may end at any time and in no order. Those are all concurrent tasks. Parallelism is multiple tasks or subtasks of the same bigger task that are run at the same time. So you can have any combination of these two things. You could have sequential execution, which is all of the code that we've written so far. So it's a single program with a single thread run on a single processor that's neither concurrent nor parallel. You could have concurrent code that is not parallel. So just like your computer, it's running multiple different tasks at the same time. but there are no guarantees on when they will start or finish. And then you could have parallel execution or parallel and concurrent execution, which both of which we will look at later in this lecture. So what does parallel execution mean? It means that you split up your computation into different parts. So you can create threads to solve each part of your computation at the same time. And then at the end, you can put them together to solve the bigger problem. So yeah, at the end, if you need to combine your results at the end, you can to complete the program. So what is parallel and concurrent execution? Well, that's your computer. Your computer spawns all of these processes, each of which have their own multiple threads. If you open up your task manager, you can see how many threads each process has. Okay, so let's move on to some code and see what this looks like in Rust. So let's try spawning a thread. When you want to spawn a thread, you need to use the standard thread crate, and then you can use the thread spawn method, and you'll pass what is known as a closure, which will contain the code that you want to run in this new thread that you've spawned. These closures are anonymous functions that you can store in either a variable, or you can pass it as a reference or as an argument to other functions, kind of like how we're doing here. So essentially, we are creating a thread, and then we're giving this thread a main function to run, and then we are continuing on with our program. So let's try and run this and see what happens. Okay, so we have the same function now in VS Code, and let's try and run this. Okay, interesting. So it seems like we're only getting the output from the main thread. Let's see if we can figure out why this is. So when we start a program, our program will finish when the main thread finishes. So it doesn't really take into consideration whether or not other threads are finished before it ends. And spawning a thread comes with a little overhead. Your computer needs to create that thread, needs to move around some data, etc. And when we're running longer running programs, these costs are insignificant and not noticeable. However, in short programs, like the one we just created, this overhead can have a significant effect, which we saw since our program finished before our thread even had the chance of printing. So we can fix this with what is known as a join handle. Join handles are returned from thread spawn, and we can call this join method on these join handles, which will block any of the code after it. So this print statement, it'll block this from running until the thread associated with this join handle has finished executing. So let's move on to creating multiple threads. It might seem pretty trivial. We could just wrap our threads in a for loop and then add all of their handles to a vector. And then we could iterate through those handles. We call join on all of them. But let's try running this and see what happens. Okay, so we have our new code in VS Code. Let's try running this and see what happens. So unfortunately, Cargo doesn't compile our code. We seem to get this error message that says, closure may outlive current function, but it borrows I, which is owned by the current or the main function. So it seems like even when we're working with threads, we have to take into consideration the rules of ownership. So when we have a thread, the thread that creates a variable, it owns that variable. So in this case, the main function owns the variable I. So when we try to move a reference to I into these threads, Rust doesn't like that due to the ownership rules and the fact that I may go out of scope before these threads finish running So to resolve this, the Rust compiler gives us a suggestion. It says that we should use this move keyword, which will either move the ownership of the variable into the threads, or it'll copy data that can be copied. So primitive types, like this integer I, will be copied into these new threads, and our program will hopefully compile. So let's try using this move keyword where the compiler tells us to, and running our code once again. And great, it seems like it has compiled, and we've gotten all of the hellos from all of the threads. However, it seems like they're out of order, even though our for loop is ordered, which seems strange. Let's try running it again. This time, it seems like we got an even different order. This is because we are not guaranteed any order when threads are running at the same time. In the future, we'll show you how to get some ordering, but for now, for the most part, when dealing with different threads running in different processors, you just have to know that you can't take order as a given. Okay, that's all for today, folks. Thanks for listening, and I will see you all next week.